here's a example like the one on quiz 7. Everybody need a copy of that? Quiz 7? Yeah. Great, so I'll just make up a few problems. Like this is U is the universe, and A and B are both subsets of the universe. So if you draw the big Venn diagram of it, you see like how they overlap and where all the rest of them are. You don't have to, but it might be nice to draw a picture of it. So let me just do that. I can point at it as I do some other examples too. So here's A and B and U. A, B. So A has x, 7, 11, 3, and 2. And I noticed that B has x, 3, and 2 also. But A has 7 and 11. B has a P. And then in U, there's some more stuff as well. Like there's a 4 and the empty set sitting in U. So U has a couple of extra items. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, there's the whole picture of the Venn diagram. Just to be careful, you might want to like put a little tag on these, just so that I know that A and B aren't elements in U. They're labeling the two round circles. So I like it. Kind of sometimes I attach them to the circles just so you can see it better. And then there's questions like find things like B minus A. So this one, there's not much work to show. You're just supposed to figure out what's B minus A is. So it's everything that's in B, subtract everything that's in A. So if you're just looking at the sets, you write down the things that are in B, but if they're in A, you delete them. So it's P, and then X is gone, the 3 is gone, the 2 is gone. That's all you got. And so if you wanted to find A minus B, it'd be the other way. You do write down the things that are in A, but delete anything that's in B. So the X will be gone. I'll keep the 7 and the 11. That's it. So here's a more complicated one. Yeah.
Is B minus A is equal to B and not A, right?
That's right.
Okay.
Yeah.
So wouldn't not A include the stuff in U? Like the not empty set and the 4?
Oh, that's a good question. So if you say the word and, when you're talking about sets, it's not real clear. I usually have to say, to make it more clear, I say intersect.
Okay.
And or union, because union means it's in either or. So it's all of them together, and you could say it's all of A and all of B. So that makes it kind of a weird ambiguity about the word and. Whereas intersection is when it's in both, just both. So it's in A and it's in B, but it's not in all of both of them. Yeah. So the what you're thinking of is where I say this is equal to B intersect not A.
Yeah.
Yeah. So it's not B union not A. That would be where you include everything in U, just intersect not A. Yeah. So that means in the picture it's just this much. It's the stuff that's in B and not in A. Yeah. Yeah. Good question though. So here's a fancier one, like the questions further down the page. You're supposed to find something like B bar intersect A minus B bar union A bar, and then put a big bar across the whole thing, like that. So remember, the bar means complement, which means everything in the universe that's not in what's under the bar. And it means take that set and then find everything that's not in it, which would be the rest of the, it's always relative to U, that's why I have to give you a U. Now, you didn't use U for these problems. These problems don't use the universe at all, they just use the A and the B. But if you ever have a big bar, then you have to use the universe. That's when the universe is important. So if you have to do something like that, you have options. Like everybody's work might turn out looking a little different, although everybody should get the same exact answer. It all depends on which rules you use from the rules, and from the shortcuts. They have like 28 of them or something. So I'm gonna guess that for most of the problems, it's that De Morgan's laws are pretty useful for simplifying because they work so nicely, and the double bar canceling, like the not cancels rule. And then after that, I'll probably just go ahead and start using my examples, plugging it in and chugging from there. So I might do, the De Morgan's laws would be where you take the big bar and break it up. So I'll break it up into B bar intersection, A minus B. And you have to be like extra careful to copy everything correctly when you're doing this. So I'll double check it. So I took that big, long, overline bar across the top. I broke it into two. But the two that you break into you break it right here over the union. That's the only place that you can break it because everything else is in parentheses. And so that union turned into an intersect, and then I took the big bar and turned it into two bars. Like, just cut it right there. Okay, so then now I can do that again on just this parenthesis. And I've also got A bar there, so that'll be simplifiable as well. When I do it on just this parenthesis, I get B bar union A minus B bar like that. So this intersect turned into a union, and this is, I'll just keep writing it, A bar. Okay, so now I'm ready to use the rule where the double bar cancels, because now they're all the same length. So the double bar over B cancels, the double bar over A minus B cancels, and I need parentheses. And double bar over the A cancels. So got rid of all the bars with that process. That might not always happen. Sometimes you'll end up with a bar that's still around. This time I just got rid of them all. Maybe I should do one more problem where they don't all disappear. But I'll finish this one. Now I'll go just fill in the B, the A minus B, since I already found it, and the A. So B is Px32. And I did find A minus B, so I'm going to turn that into 7 and 11. And I need to intersect that with A itself, which is x7, 11, 3, 2. So I went ahead and filled in the sets. If I hadn't already found A minus B, you could do that in your head at this point and do all the things that are in A, but cancel the things in B, so I get just 7 and 11. And so now, the union means that I keep everything in there. So, B, X, 3, 2, 7, 11. And the intersect means that I'll only keep the things that are in both. X, 7, 11, 3, 2. So, looks like I keep everything but the P, since intersect is just the stuff that's in both of those. So I have the X, the 7, the 11, the 3, and the 2. That'll be my final answer. It'll be X, 7, 11, 3, and 2. The order of that answer doesn't matter. Like the listing can be any order as long as it's the same collection of elements. There you go. So, yeah. So maybe one more would be just for practice. Find just B bar. Okay. Since what's in that? Okay, so that's B bar. Since I didn't have, I thought I was going to have to do that in this problem, but then all the bars canceled completely. Any question about the that big problem though? See how I canceled all the bars out on that one? They just all turned into double bars as I did the Morgan's laws. So if I just had to find B bar, I just look at whatever B is and delete it from U. So P, X, 3, and 2 are all gone. So I have P, X, 3, 2 gone. Oh, just the last half of it. So 7, 11, P, and 4. Empty set. Yeah. That's what's not in B. Those 4 items. So that's a much shorter one, obviously. So it's a mix of long and short ones, so that you have to do somewhere simplifying is helpful. All right. So counting. The counting shortcuts that we have so far. So first off, counting just by hand means that you just count the number of elements, the top number of elements. That's what. That's when you have A. It's just the number of elements. All right. So the shortcuts we have is, first off, if you have the empty set, that means there's 0 elements. That's what the empty set means. It's the one that you can also write as just 2 curly brackets next to each other. This is where we left off last time, so you have some of these in your notes already. I'll add some new ones though. Then we have this the power set, which is the set of all subsets of A. And if you want to count how many of those there are, it's a power of 2. But you put the original number of elements as the exponent on it. Then we did the Cartesian product. And that shortcut is that you can just directly count the 2 smaller sets and then multiply those numbers together. I can't remember if we did this one yet. The next one that goes on this list is for union. If you have A union B. And yeah, no, we didn't do this one. I think I may have done a similar one. But this one, if you have A union B, the shortcut for it is, instead of having to count them all, you count the ones in A, then you do plus, and you count the ones in B. But then you have to do this. You have to subtract A intersect B. So actually that one doesn't look like much of a shortcut, except a lot of times there's going to be problems where there's millions of things. And so it is a shortcut if you can find the 3 pieces easier than you can find the big answer. So, but you can see it in like a small example right here. Here's why, and this explains why you subtract the intersection. Like in this example, A union B is everything that's in both circles, right? So not the 4, not the empty set, but 1, 2, 3, 4, 5, 6 items. the 7, the 11, x3, 2, and the p. So, in our example, A union B, if you're counting them, would be equal to, better come out to 6, but I'll go ahead and say it's A plus B minus A intersect B. So what's in A would be just the 5 items, 7, 11, x3, and 2. Just looking at A, there's 5 things in there. And in B, I gave it over there, there's 4 items. And in A intersect B, there's 3 items, x3 and 2. So that does come out to 6. That's good, because you can also do it by just figuring out what's in A union B. You can say 4, it equals, what's in A union B is everything except for the 4 and the empty set, so 7, 11, x3, 2, and p. And yep, there's 6 things in there. So, for an easy little example, that's not much of a shortcut, but it is going to be very useful later. And here's why it works. If you count all 5 of these items and all 4 of these items, and looking at the picture, I just counted everything in the big circle here, 1, 2, 3, 4, 5, and I counted everything in the second circle, 1, 2, 3, 4. But I just counted everything in the middle twice. So if you count all of A and all of B, you count the stuff in the middle 2 times. So to make sure that I didn't count it twice, I just have to subtract it once. So x3, 2, I subtract the 3. 3 got double counted in there. It's counted in, there's secretly a 3 in here and a 3 in here. So if I get rid of one of them, then I'll have the right number of items. So that's why that works. Subtracting the intersection just means subtracting the things you counted double. So there is a shorter version of that. It's pretty nice if there's no intersection, like no overlap. You can say if, so you say 4 implies 5 here. Put the arrow pointing down 5. 4 implies 5. And 5 says if the intersection is empty, like there's no overlap at all, that's the empty set, then the count of the union is just addition straight up, which is pretty clear using number 4 and number 1, because number 4 works no matter what. That's always true. And but only in the case where the overlap is empty. Then number 1 says that the overlap has 0 things in it, so it comes out just A plus B. Similarly, for subtraction, number 6 is A minus B. So, if you want to know how many things are in A minus B, it does work like subtraction. You can take A and then minus. There's a couple of ways to do this. I think one of the ways that I'll do it is that I'll just say A minus B is always equal to the number of items in A minus the number of items in A intersect B. So you can see that over here, like A minus B was 7 and 11. So if you want the number of items in it, it's all of them minus the ones in the intersection. So 2. But number 6 implies a nice number 7, which is if one set is a complete subset of the other, then subtracting the smaller subset is exactly subtraction. Because if one is a subset of another, then their intersection is the whole small set. So you can just subtract it all off. So, like number 5 and number 7 there, where you have an if statement first, those make nice shortcuts. You can just do straight up addition or subtraction, but you have to check something first. You have to make sure that there's no overlap, or that one is entirely contained in the other. So, one more counting shortcut then. I didn't use anything with the complement yet, but if you do, it's really just the same as the subtraction ones, because the complement, where you put the bar over it, is the same thing as the universe minus it. So we wrote that before. A bar is equal to the universe minus A. So you can just do that inside of the double bars. And then you can use number 7. Any set is a subset of the universe. It has, if I'm going to call it the universe, it has to be true that every other set is a subset of it. So that means I can just do the total number of items in the universe minus the number of items in A, like I did for number 7. So number 8 is sort of also a duplicate of number 7, but it's a special one. And so that's it for chapter 6. Chapter 6 is done there. We should do one example, maybe using some of those shortcuts. Let's see. I'll leave the same set examples. So maybe you'd have to solve a problem where you do use a couple of those rules. So for an example, where should I write it? Maybe I'll squeeze it over here. It's still dark there, isn't it? It's okay if I write large. Hopefully. So for an example, same sets. Right. So I won't change my sets at all. I'll say find the number of items in the power set of A crossed with just B for now. So that says find the cardinality, or find the number of elements of, and then you look inside and it's got the power set of A and it's got crossed with the set B. So it actually, I could use 2 and 3 here. But first I have to use number 3, because the crossing is happening, like that's the bars are not right around power set of A. If I had cardinality of the power set of A, that'd be great, but I don't have that yet. I have the cardinality of the cross product of the power set of A and B. So first I have to use number 3, so I'll do that. Power set of A, bars, times, I'll make it a times B. So I use number 3 there, where I'm putting that dot in there for a times. It's like, rarely do I use a dot for multiplication, but if if you use parentheses, it's confusing. And if you write the two things right next to each other, then you have like a double bar in the middle and it looks weird. So that's times. Now I can use number 2. So I use the rule 2 there, and it says, or shortcut 2, 2 to the A times B. And then I can look at my my sets and count how many things are in there. A has 5 things, B has 4 things, right? So it's 2 to the 5 times 4. I'll put parentheses. So that's 32 times 4. So 32 times 4 is 128. Right. Oh man, that's familiar. I bet that's very similar to the problem you had to do. I bet I gave away some of a future quiz. You didn't have to do this on this quiz that I just passed out on Friday, do Wednesday. But there is questions like this on the next quiz, so write that one down. Yeah.
I have a question. When you get a set consisting of like 2 and 8, and you subtract out of the set consisting of 5, what would the result be?
Are you talking about the empty set?
No, so like if you had so you're subtracting 2 sets, but like you don't have any numbers in common, so one set is like 2 and 8, the other set is 5.
Oh yeah, like just if you have like C equals 2 and 8, and D equals 5, and you're supposed to find C minus D. Yeah, it just says everything that's in the first one minus anything that's in the second one, so you get back everything. Yep. So you can, that's a general rule. If there's 2 sets that don't overlap, then subtracting doesn't change the first one. Yeah.
Thank you.
Sure. Yep. Say if C intersect D is the empty set, and then C minus D equals C. Subtracting the empty set. Yeah, great. So, any question here? Or are these? So, yeah.
Does the complementary bar won't affect if there's an intersect or a union in parentheses?
Let me see. I want to say it does affect it, because if you use the De Morgan's laws, you have to do 2 things. You break the bar, and you flip the union to intersect. So,
Give me an example like that.
yeah. So, I guess what you have to do is you have to just do it in stages is the main thing. Like, you can't immediately change anything that's under here. You don't do it until you break it. Yeah, then you flip it. Right. So yeah, don't do any flipping until you break right above that symbol. Yeah. You can break the bar for complement over a symbol, but then you flip the symbol. And it's very much like when you have something like not, and then there's a statement P and Q. What you do, breaking the bar is like distributing the not. So you do not P or not Q. It's the same exact rule actually. One of them implies the other. You can just write statements about the sets and then turn the statements about the sets into complement, and it works out. But yep, that's it for chapter 6. So chapter 9 is a real smooth transition though. So I'm skipping straight to chapter 9 because of that, because it makes a nice smooth transition. So chapter 9 though is still counting that's what those counting shortcuts are doing, counting the number of elements in a bunch of different sets. The power set, the Cartesian product of set, the union of sets. So what's the difference here is that these sets in chapter 9 are more complicated. So that one thing you could say, counting the number of elements in sets that are more complicated, but specifically, there's sets of something. Number of elements in sets of combinatorial structures. So what that turns into is big words there, but what it means is that there's sets that come from a word problem. It means that there's a description of what's allowed to be in the set. Like you say, here's what the set is, and you describe it with some rules. And then you have to figure out how many things that are in it. So I'll define what a combinatorial structure is. But the other word for this is just combinatorics. So, yeah, and it has in the word what it means. It means combinations. But combinatorics is a little hard to find in a lot of dictionaries, and even in spell check it still doesn't know for some reason, although it's the title of millions of books, combinatorics. It's a common textbook. So here's what it means. A set of combinatorial structures is a set that we get in two steps. So number one, we're given a set. And so you're always going to be given something. Well, so it's a set that you're given, and it's a set of building blocks. I'll put quotes around that though. Because we're going to use the building blocks to build the structures in the next level. But so what kind of things can be building blocks is pretty broad. It's just any set at all, really. So the building blocks can be numbers, they can be letters of variables, they can be shapes. So here's a few of the things. It's basically anything that you can make in a set, but numbers, I'll just let you know, there's nothing special about them. It's the same list as I put up before. Numbers, letters, shapes, things like points, like points AB or points XY. Lines. Oh, they're all anything really. So Okay. So you're given a set, and you're told these are your building blocks, and then you're also given some rules about how to construct them. Rules for how to build a structure. Using the building blocks. Put the double quotes on that again. Actually, we have definitely seen examples of this already. Here's the first one I can think of is, or these two rules, 2 and 3. For the power set one, the building blocks are just the original set A, and then the structures are real simple. The only thing that it says is that you build a structure by picking any subset, any smaller collection of them, and that's your structure. So these don't have to be complicated structures, but they can be. So let's see. Here's here's a list of example structures. Structures can be subsets. I'll make that one especially. Lists. Any sort of data structure, like arrays and so forth, or any JSON. Any JSON structure. JavaScript object notation, and in fact, it could be any programming object at all. And actually it's much broader than that. You can think of a structure as being anything that you build out of other stuff. So it could be like molecules in chemistry, and circuits that you build out of wires and stuff like that. Computer networks like the internet. Oh man, it just goes on and on. So, as long as you've got some building blocks and some rules about how to stick them together, that's what structures, combinatorial structures are. So, that's why it turns into a much more exciting problem than we have here in these eight shortcuts. The problem is that it can be really tough to figure out how many possible structures you can build out of some building blocks. Most of the questions that you can ask about it are completely unsolved, as in it's a research problem that if you figure it out, you get your PhD. You can start with some easy questions though, like for an example, the building blocks are A equals, what was my list? It was like the 5 things, 7x, 11, 3, and 2 or something. Yeah. Just keep that same example going. The structures are any subset. So the subsets of A. That's a structure. And then the question is, how many structures are there? And we know that's that number 2 there. How many subsets are there? And the answer is 2 to the A, or 32. Or you could use the notation for the power set with bars around it. And then you can use the counting the shortcut and get 32. And then number 3 is another example. There you've got the building blocks could be A and B, or the set of A and the set of B, or the set of the 2 sets A and B. So the 2 building blocks are the 2 sets. And then the rules are pick anything from the first one and anything from the second one. But actually, I'll switch to a word problem kind of situation to make it a little more general. Let's see, I've got time for one more. So they have a lot of times the structures are like a real life situation, and the building blocks are things that you have to choose from before you put them together. So for this example, I can start out by just saying how many ways of like a menu order. So how many ways can you order a pizza? Where? And then I'll limit this so it'll go pretty fast. There are exactly 3 crust options. So maybe regular, I'll put the seltzer. Regular thin crust or cheese stuffed crust. And there's 2 sizes. So just go with a large and small. And toppings. Okay, so 4 toppings. Options. Okay, I'm running out of time to think, so I'm just gonna call pineapple. That's a good one. And then if I use pepperoni, they'll both start with P, so that's a problem. Too many of them start with P. I'm just gonna go with topping 1, but you can pick your favorite. If you like pineapple, that's topping 1. Topping 2, topping 3, and topping 4. Let's give them numbers. So whatever your favorites are, that's what they are for you. All right. Yeah, we're also getting close to lunch here, so it's bad to use a food example. Yeah. Okay. Pineapple and pepperoni are both good. So, but they both have P. So I wanted letters that you can use in the picture. Okay. So those are my building blocks. These 3 sets are the building blocks. It's a set of sets. So you're given those. So now you just need the rules, and so let me make the rules real simple. You just have to pick one of each. You can't have 2 toppings, for instance. So you just have to, the rule is a pizza can only have 1 topping, 1 topping, 1 size, and 1 kind of crust. You can't mix and match anything. Now that's something that will add more complicated problems soon, right? Where you can add to it and say you can pick 2 toppings, but let's go with 1 of each. And then the structures are the pizzas, or the pizza orders. You know, it's the actual pizza if you build it, or you can just plan for it, put it down on a piece of paper. So then the question is, how many ways can you order it? And this is where it's nice to draw a picture of this so you can see why it works. At least once if you haven't seen it recently. Almost everybody has seen something like this or tried to figure it out on their own. But a decision tree shows you exactly why the multiplication principle works here. So the decision tree is where you just draw the options as branches for each decision. So first decision would be draw kind of large. Pick a crust maybe. So that's where I was trying to get things that were easily abbreviated. You got the cheese, the regular, and the thin. And then the second decision is to pick size. And picking the size is that whole vertical line there, because you pick the size no matter what crust you pick, you have to pick a size too. So, pick a size, and each time it's small or large. So large or small, large or small, large, small. And then finally you have to pick a topping. Only one topping allowed, so 1, 2, 3, 4. There's the 4 topping picks. This is where, if there's any more options than that, the decision tree would get too big. And you may not have room on your paper anyways. I have a whiteboard to work with. You can do an abbreviation if you want, if you know what it means. So 4 toppings every single time. Any way you pick the crust and the size, you still have the 4 topping pick. So that's what this decision right here is. Pick a topping. Now you can see the whole structures. The leaves of the tree, they represent the structures you can build. And the number of them is easy to figure out. There's 3 main branches, and each of them has an identical sub-tree. And then for each of those, there's 2 branches, and they have identical endpoints. So you can say there's 3 main branches, and they're each turn into 2 choices, which each have 4 branches coming out. And so that equals 24. Total structures. I mean, or you could just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. If you draw it carefully. But the point is that you can multiply them, because every decision you make doesn't affect the other decisions. It's independent. So you still have the same number of options no matter what you do the first time. So I'll stop there. I'll make a point of starting next time with one where you have slightly different options available, like that they say, you can't have a small cheese stuffed pizza, you have to get the large or something like that. So, good place to stop though.